biggest problem with traditional AI is that it is slow, dependent, and constantly sending your personal data to the cloud. Whether it's a smart camera which is identifying the intruders, or an autonomous vehicle taking the real time decisions, or a factory sensor which is detecting the equipment failures. All of these rely on the cloud to think for them. And that reliance, it can cause privacy breach, cyber leaks, or in life critical embedded systems like medical equipments or vehicle safety control. A simple delay or a network failure from the cloud can cost lives. But what if devices could think for themselves instantly, securely, and offline? And that is exactly what edge AI technology enables.
AI at the edge. Edge AI will break us free from encapsulated cloud-based use cases. So AI at the edge,
So we don't take an approach of edge versus cloud.
where the AI meets the physical world.
So now in this video, we will explore how Edge AI solves this critical bottleneck, how it compares to cloud AI, and how powerful AI models are now running on a microcontroller and embedded processors right where the data is being born. About a device that doesn't just collect data but understand it right there on the spot, and that is the essence of Edge AI. Instead of relying on the internet connection and sending data everything on the cloud, the device itself, whether it's a tiny microcontroller or a powerful embedded processors, and running the AI algorithm locally, it senses the environment, processes the data, and makes the decision instantly, all ever without going to the online. That is the real power of edge AI, enabling the intelligence right at the edge where the data is born. Lightning fast responses, increased privacy, and true independence from the cloud and the server cost. Let's say you have a smart camera in a factory watching the defects on a fast moving assembly line. In a traditional cloud AI setup, that camera sends all its footage to the cloud, and the server processes it, figures out if there is something wrong, and sends the result back to the camera. But by the time it happens, the faulty product might have already missed. Now enter the edge AI era. Instead of sending data to the cloud, the AI models run right inside the camera itself. It sees the defect and processes it and gets the result instantly and act on it on a real time. No internet delays, no privacy concerns, no wasted bandwidths. Just smart decisions right where the data is born. So now you all must be wondering, where does all this edge AI magic happens? And the answer lies on embedded chips which are there in the heart of your devices. MCUs, which are stated as microcontrollers, small, ultra low power brains found from smart meters to home appliances to sensors, or the MPUs, which are stated as microprocessors, more powerful chips which are found in gateways, CCTV cameras, or the automotive ECUs. These are the platforms on which AI models are being deployed, and they are transforming from energy systems to industrial automation. But here is the thing, guys, running the heavy compute AI models on these tiny chips is not so easy thing. It follows an optimized three-step pipeline to bring intelligence to the edge. Let's get into step 1, training and development of an AI model. This is a standard first step that every AI engineer does, building and refining the models on host machines using powerful, widely accepted AI development platforms. We begin in the cloud or a workstation, training the deep learning models like YOLO, MobileNest, or ResNet using frameworks such as TensorFlow, PyTorch, or Keras. Or in many cases, we also train the machine learning models like Random Forest, SVM, or XGBoost for a structured data and a time series patterns. And here we work with the large data sets and heavy compute to help our AI models understand the patterns like detecting the objects, reading the meters, or classifying the audios. And in this, the tools which are used are like of model training frameworks like of TensorFlow, PyTorch, or Keras. And then comes the dataset platforms for AI model training are sourced from either standard platforms like Cuckoo and ImageNest for computer vision tasks, UCI machine learning repository for structured and tabular data, Or comes the custom sensor data sets for domain specific applications like industrial, automotive, or energy systems taken from the real time sensors of these specific applications. And now comes the step two, convert and optimize the AI model. Once the model is trained, it is often too big and complex for embedded devices. So, next, we convert it into a lightweight format using the AI model compilers and optimization tools. For instance, TensorFlow Lite converter is used to convert the AI models to the format of TFLite format, which are lightweight AI models for microcontrollers. Tools like TVM, Vela, or OpenVINO are further used for compressing the models, prune the layers, and quantize them to 8-bit integers without losing the accuracy. And in these steps, tools which are used are of AI model converters and optimizers like TFLite converter, ONNX, TensorRT, TVM, OpenVINO, or ARMVela. And AI model tech optimization techniques like quantization, pruning, and layer fusing. And then comes the step three, deploy the AI model onto the edge. Now it's time to bring the trained AI model to life directly onto the edge device. We deploy the optimized AI model onto the MCUs, MPUs, or NPUs using a specialized inference engines, lightweight runtime environment designed to execute AI models efficiently within a limited resources of embedded hardware chips. And these inference engines ensure real-time decision without cloud dependency, enabling secure and low latency AI processing right where the data is generated. Common inference tools and runtimes which are used in this step are like ARM-CNN for ARM Cortex-M MCUs, optimized neural network kernels for low power and memory optimized microcontrollers. Another is TFLite Micro for small microcontrollers other than ARM Cortex MCUs, stripped down version that runs on bare metal or RTOS based systems, or NXP EIQ toolkit for I.MX RT or the STD2K series of MCUs and MPUs of NXP semiconductors. These are the NXP dedicated AI enablement suite that supports model conversion, optimization, and deployment for NXP semiconductor MCUs and MPUs. Another one is ONNX runtime or the TensorRT for MPUs like of I.MX or the x86 Edge NPCs. These are the cross-platform high-performance inference engines supporting models trained in multiple frameworks. And now, what happens next? These quantized and optimized AI models, TF-Lite format, .ONNX format, or converted binary blob is flashed into the target MCU or MPU. And that is where AGI truly begins. Running locally as these MCUs or MPUs are connected with real-time environment or the physical sensors that are connected collecting the data at the edge. So from training complex models into the cloud to deploying them onto the tiny chips, and that is how the AI comes live at the edge. No servers, no delays, just real-time intelligence right where data is born. And that is the power of edge AI, fast, secure, and built for the real world. In our upcoming videos, we will deep dive into the real world edge AI use cases across the industries, from smart energy meters to factory robots to automotive issues to industrial automation. We will also explore the full ecosystem of tools, frameworks, and chips from TensorFlow Lite to the NXP EIQ platform to help you build and deploy your own intelligent edge AI solutions. So, if you're excited to explore the full potential of edge AI technology, just not just from use cases but from the implementation level, subscribe to our YouTube channel, share this video to the maximum people so as to aware them about this amazing tech of edge AI, and be ready to be skilled engineer and not just graduated one.